Hackenbush is a game played with a bunch of colored branches on top of a ground. Two players, we'll call them blue and red, take turns chopping down their branches. After each chop, any branches left floating in the air fall to the ground and go away. The player that makes the last chop wins. This simple little game was one of many such games that were studied extensively by Elwyn Berlekamp, John Conway, and Richard Guy, three of the most brilliant mathematicians of our era. Hackenbush is what's called a combinatorial game, meaning basically that it involves two players with no luck or secret information, so there's always an optimal strategy for each player that we can figure out and study. Games like chess, checkers, Go, tic-tac-toe, dots and boxes, and so on all can be thought of as combinatorial games. And it was through studying games like these that Berlekamp, Conway, and Guy discovered a vast and wondrous new world of mind-boggling math, which they went on to document in their comprehensive 4-volume magnum opus. Winning Ways for Your Mathematical Plays is the definitive almanac for this new world, giving life to it and its fascinating alien inhabitants with a kind of whimsy and creative passion that all mathematicians should aspire to. Uncharted new number systems with strange properties and wacky operations, all presented in an illustrated chapter book with charming and humorous commentary that would make Lewis Carroll proud. But the playfulness of the writing really serves to mask how groundbreaking the material actually was. These are some of the foundational texts of combinatorial game theory. The books tackle a huge variety of games, each of which gives rise to new bits of math and fills in part of a much wider picture that we're still exploring to this day. But it all started with Hackenbush. To get a handle on Hackenbush, we'll work from the ground up, and you can hardly start simpler than a single blue branch. Obviously, if it's red's turn here, they lose immediately because they have nothing to chop. If it's blue's turn, they can chop their branch and win, since red is once again unable to play. So this position is a win for blue no matter whose turn it is. Likewise, this position with only a single red branch is a win for red. What happens when you combine the two positions together? Now things aren't so one-sided. If it's blue's turn first, they have to chop their branch, and after red chops theirs, blue is out of options and loses. On the other hand, if it's red's turn first, blue gets to make the last chop. Whoever chops first in this position ends up losing. Another way to think about this is that the blue and red branches balance each other out, and neither player has an advantage. We can add another blue branch to this position to bias it back towards blue. Two blue branches to one red means that blue's first chop will take us to the position we just saw, where red, being the player to move, will lose. Giving red another branch here will restore the balance. This position is once again a win for the second player, whoever that happens to be. In fact, it's not too hard to see that if we have any number of blue branches and red branches situated like this, the winner will be whoever has more branches, and if it's a tie, whoever plays second. The story is similar if instead of piling up branches horizontally, we do it vertically like this. In this position, there are once again two blue branches and one red. Blue has a choice here. They could, if they wanted to, chop the bottom branch, but this would be a mistake, since their top branch would go with it, and they'd be left with no response to red's next play. More sensible is to chop from the top down, so there's no collateral damage. If both players do this, the winner in these kinds of positions will once again be whoever has more branches. Okay, whatever, pretty boring stuff, but we're laying the foundation for everything that's coming. Some positions in Hackenbush are biased towards one player, and some others are balanced in the sense that they favor whichever player doesn't have to go first. Now we're ready to make things a bit more interesting. Let's go back to the single blue branch, and let's try adding a red branch on top of it. Who wins here? Well, if it's red's turn, chop, chop, blue wins. If it's blue's turn, they chop their branch, the red one goes with it, and blue wins even quicker. Once again, blue wins no matter who goes first, just as if the red branch wasn't there. Turns out the red branch didn't really do much, did it? Well, if it is useless, and the single blue branch is all that matters, then we should be able to counterbalance it with a single red branch here, just like we did before. Now if blue goes first, chop, chop, red wins. But if red goes first, they can chop this branch up here, and now it's blue's turn in this balanced position, meaning red still wins. This time, not only was blue's initial advantage neutralized by the extra red branch, but it actually tipped the scales in red's favor. In other words, this blue-red tree is not worth as much to blue as the single branch is to red. So how much is this tree worth? Well, we can test it by continuing to try to restore the balance. Let's add another copy of this tree, so now we have 2 of these trees for blue, versus 1 branch for red. Who wins here? It's a bit more complicated, but if blue goes first, they have to chop down one of the trees, after which red can win by chopping here and reaching this position with blue to move. And if red goes first, those same chops happen, but in reverse order, and red is the one who ends up losing here. So whoever has to chop first loses, and this is a balanced position. 2 of these trees together are precisely enough to counterbalance 1 branch. What does that mean about the single tree then? Could you maybe say it's worth half a branch? Now hold on, I know what you're thinking. A branch is a branch, you can't say it's only a half. Well then, let's stop talking in terms of branches and try just using numbers by themselves to describe positions. Let's say the position with the single blue branch has a value of 1, and adding more blue branches increases the value to 2, 3, and so on. Conversely, the single red branch will have value -1, and subsequent red branches will take us to -2, -3, and so on. The blue-red tree we just talked about will of course have value 1/2, because 2 of them together are worth the same as a single blue branch, which has value 1. What about a position like this one? We've already seen that it's balanced in that it's unbiased towards either player. But we can also think of it as being the combination of these 2 positions, worth 1 and -1. Everything seems to be pointing towards 0, and indeed 0 is the value of not only this position, but all such positions where whoever moves loses. These 0 positions are quite important because if at any point you can reduce the position to a 0, you win, because your opponent will be the one who has to move. The keen among you might have noticed a pretty big assumption we're making here, which is that the numeric value of a position is just the sum of the values of its component parts. Can we really add positions like this, the same way we add numbers? The answer is yes. In fact, one of the central ideas in combinatorial game theory is adding positions together, and they can even be positions from entirely different games with different rules. That's a whole separate topic though, and beyond the scope of this video, but what it means is that if you have a Hackenbush position like this, with a bunch of separate components, and you know the values of each of these components, you can just add them together to get the value of the whole position. Moreover, once you know the value of a position, you can immediately figure out who wins with optimal play. If the value is positive, it's a win for blue. If it's negative, it's a win for red. And if it's 0, then, as we discussed, the position is a win for the second player, whoever that may be. This idea of assigning numeric values to game positions is the essence of combinatorial game theory, and you might be wondering if any position in any combinatorial game can be encapsulated in this way by a number. And to that, I would answer yes, provided you extend your idea of what a number is so far beyond your wildest imagination that you'll never look at math the same way again. But we're getting ahead of ourselves. Let's stay on track and take things as they come. It's simple to construct a Hackenbush position with any integer value. Just pile up that many blue or red branches. We've also just seen a position with a fractional value 1/2, and we can swap the colors to get an analogous position with value -1/2. Are there positions with other fractional values? Let's try taking our 1/2 position and adding another red branch on top. Adding the first red branch reduced the position's value from 1 to 1/2. Will this second red branch perhaps bring it down to 1/3? Or 1/4? Or even 0? We can rule out 0 right away. Obviously, blue is still the only one who can win this position. To decide between 1/3 and 1/4, we can try adding 2 copies of this position to the -1/2 we saw earlier. If we call this position x, then our new position is x plus x minus 1/2. If x is 1/3, then that will work out to be 1/6. Positive, meaning blue would win no matter who goes first. And yes, if red goes first, blue has a couple ways to win, this one being the quickest. But it turns out that if blue goes first, all these red branches up here are just enough to give red the win. The value of this position is 0, meaning x is 1/4. Swapping the colors of this tree will naturally give you negative 1/4, which you can then combine with this one branch to produce 3/4. Alternatively, you can produce 3/4 by augmenting this 1/2 tree with an extra blue branch, as opposed to a red one. This is less obvious, but you can check that combining this 3/4 with a 1/4 is enough to counterbalance a negative 1. Multiple positions can have the same numeric value, just as earlier we saw many ways of producing a position with value 0. So we got fourths, what about eighths, and 16ths? Well, it just so happens that you can produce any fraction like this with a simple stack of branches, which the authors of Winning Ways demonstrate in this cute number line illustration. Fractions like these, where the denominator is a power of 2, are called dyadic fractions, and they're often the simplest ones to produce in a combinatorial game. But non-dyadic fractions like 1/3? Well, we'll come back to that. It's kinda wild how easy it is to test things like this. You're basically making discoveries and solving algebraic equations by playing games. You have a position, and you want to find out if it's positive, negative, or 0? Just play it out and see who wins. You want to find out its precise value? Just try adding other stuff to it until it becomes balanced. This back and forth between numbers and outcomes is important to stress again here. Positive positions are biased for blue, negatives are biased for red, and a 0 means that the position is balanced in that whoever goes first loses. If that's all clear to you, great, because pretty soon, things are going to get a little more confusing. In this position, there's not only blue and red branches, but also green branches, which can be chopped by either player. Positions with just blue and red branches are often frustrating because there's never any incentive to move. Being forced to chop one of your own branches is always kind of a concession. Green branches are game changers because now having the first move can actually be a good thing. For example, take a look at this position with a single green branch. Whichever player goes first will be the one to chop it, leaving their opponent with nothing to do. What's the numeric value of this position? There's obviously no bias towards blue or red, so is it 0? Not quite. Remember that in a 0 position, whoever goes first loses, but in this position, whoever goes first wins. The value of this position is not positive, not negative, and not 0. So what is it? It's here that many of us might just give up and accept that this convenient theory of assigning numbers to positions has its limits, and we should have quit while we were ahead. But the most stubborn among us might say, what if it's not our theory that's limited, but numbers themselves? What if this position does have a value, but it's just a number we've never heard of, beyond our broadest horizons? Somewhere out there, like a distant star, only detectable through its influence on what's around it. In fact, let's call it star, and let's shove it into our number system and see what happens. In this position we have a green branch next to a red branch. Let's say the green branch does have a value of star, then the whole position has a value of star minus 1. We saw that either player could win with the green branch by itself, but adding the red branch turns out to be more than enough to give red a decisive advantage. Whoever goes first will chop the green branch, and red will be the only one with a branch left. Evidently, star minus 1 is negative, meaning star is less than 1. Adding a blue branch on top of the red one doesn't help either. Remember that this red-blue tree has value negative 1/2, so the whole position now has value star minus 1/2. But red still wins, and just as easily. Star minus 1/2 is negative, meaning star is less than 1/2. In fact, we can add as many blue branches as we want, and the situation doesn't change. All of these positions are wins for red, meaning star is less than 1/4, 1/8, 1/16, and so on. And by similar reasoning, we can show that star is greater than -1/2, -1/4, -1/8, and so on. Star is less than all positive fractions, and greater than all negative fractions. Just like 0. But it's not equal to 0, and it's not greater than or less than 0 either. Star and 0 just have kind of a complicated relationship. We can go through a similar process to figure out that, say, 1 plus star is in the same neighborhood as 1, but not equal to 1. In the vernacular, we say numbers like 1 plus star are confused with 1, or sometimes 1-ish. And yes, that is the technical term. Every number x on the real number line has one of these star friends, the number x plus star, which is confused with x, but not equal to it. What about star plus star? Well, let's test it using this position with 2 green branches. Here, whichever player goes first has to chop one of the branches, and their opponent will win by chopping the other. This is a second player win, meaning star plus star equals 0. This means whenever you have 2 stars in a sum, they cancel out. In other words, star is its own negative. It's as if star is to addition what -1 is to multiplication. We saw that combining blue branches horizontally has the same effect as stacking them vertically, and likewise with red branches. You might assume that green branches work the same way, so this 2 stack would have a value of star plus star, and the 3 stack would be star plus star plus star, and so on. But the reality is not that simple, and you can start to see that by just looking at the stacks. Star plus star is 0, but clearly this 2 stack is not a 0 position. Whoever goes first will simply chop the bottom branch and win right away. Like the 1 stack, the 2 stack is a first player win, meaning it's neither positive, negative, nor 0. Is it star? Well, if it were, then adding another star to it would give us 0. But this position is not 0 either. In fact, it's another win for the first player, who can start by reducing it to 0 like this. So the value of this position is once again not positive, not negative, and not 0, and it's also not star. We've run out of numbers again. Well, screw it, let's call this one star 2. It turns out that there are infinitely many such star numbers, star 3, star 4, and so on, each one being the value of a stack of that size. All of these star numbers lie in this same tiny neighborhood between the negative rationals and the positive rationals, but they're all confused with 0, and with each other. Like star, each star number can also be added to any real number x to produce a number that's confused with x in the same way. All this is weird enough, but what's really wild is what happens when you try adding them to each other. The simplest case, as we'll see, involves 2 identical stacks. Here, the value of each stack is star 3, so the whole position is star 3 plus star 3. What happens when we play it out? Who wins? Feel free to pause for a bit and see if you can figure out a strategy for either the first or the second player that guarantees a win. The answer, as you may have found out, is pretty elegant. The second player here can exploit the symmetry of the position by simply copying whatever the first player does but on the opposite stack. The first player always loses in the end, so star 3 plus star 3 is 0. And there's nothing special about 3. The same strategy can be used for any 2 identical stacks of any size, so each of these star numbers behaves just like star in that adding it to itself gives 0. In short, every star number is its own negative. If you're familiar with the game Nim, you might have noticed that this is basically the same thing. Nim is traditionally played with heaps of coins or matchsticks, but the mechanics are identical, and the solving of that game actually predates Winning Ways by almost a century. As such, these peculiar star numbers are usually called Nimbers because of the pivotal role they play in Nim. Let's make an addition table with some of these Nimbers. We can fill in the 0 spots. Don't worry, 0 is still an additive identity in our new reality. And we also know from our experiments that there are zeros all along this diagonal. We have 6 spots left to fill, and as it happens, we can take care of them all in pretty much one fell swoop. Here's a Hackenbush position with 3 green stacks. With a bit of trial and error, you can verify that this is a 0 position, because no matter what the first player does, the second player can reduce the position to 2 identical stacks, which we know now is a win for them. What does this mean? It means that star plus star 2 plus star 3 equals 0. And since these numbers are all their own negatives, we can express each in terms of the others by just moving it to the right side of this equation. Star plus star 2 equals star 3, star plus star 3 equals star 2, and star 2 plus star 3 equals star. The computer scientists among you might notice that this looks a lot like the table for bitwise exclusive OR, and yes, that is exactly how number addition works. To add, say, star 5 and star 12, you write the numbers 5 and 12 in binary, line them up like this, and then create a new binary number with zeros in all the spots that match up and ones in the rest. If you can do this in your head, you'll not only be unbeatable at Nim, but you'll be most of the way towards mastering all green Hackenbush, which means now it's time to bring back the blue and red branches. Here's a flower with a leaf, a stem, and a blue petal. If it's blue's turn, they can win by chopping off the petal and reaching a 0 position very similar to the one we saw earlier. If it's red's turn, they unfortunately have to chop either the stem or the leaf, allowing blue to win by chopping down whatever's left over. Blue wins either way, and this flower is positive. Finally, no more of these dang confusing Nimber things. So how positive is it? Well, let's try adding a single red branch. Now all of a sudden, no matter who goes first, no matter who ends up chopping the last bit of the flower, red will save their extra branch for last and win easily. Evidently, flower minus 1 is negative, so flower is less than 1. And wouldn't you know it, it's also less than 1/2, and 1/4, and 1/8, and so on for the same reason. In fact, it's less than all positive rationals. But it's positive! It's greater than 0. Like star, the value of this flower is a new number, and it has a special name. It's called up. Here's a similar flower with a red petal. We can use the exact same logic here to determine that this position is a win for red, meaning the flower has a negative value, but it's greater than -1, -1/2, -1/4, -1/8, and so on, while still being less than 0. As you might have guessed, we call this value down, and it's equal to negative up. You can see pretty easily that when we add up and down, we get 0, since whoever goes second in this position can just copy what their opponent does. Up and down are numbers in our system, and they can be added to, subtracted from, and compared to all the other numbers we've seen. This position, for example, has a value of 1 plus up, and this one has a value of 1 plus up plus star. What about this one? We have two flowers, each of which has a value of up, so together they're up plus up, which we call double up. We can keep adding ups and go as high as we want, and because up is positive, these numbers will keep getting bigger and bigger. But they're still all less than all of the positive rationals like 1, 1/2, and so on that we're all familiar with. No matter how many hundreds of flowers you have, one red branch is still enough to overpower them. Who wins in this position, which has a value of up plus star? You might assume that since up is positive, up plus star has to be positive as well, meaning blue wins even if red goes first. But a quick check will show that no, whoever goes first can win by chopping the stem of the flower and reaching this familiar 0 position. Up plus star is another one of those confusing positions which are not positive, negative, or 0. It's also not star. In fact, up is confused with star in the same way that 0 is. Here's a table with green legs and a blue surface. It looks different from the flower, but if you toy around with it, you'll find that the game plays out exactly the same. Blue has the advantage, but it's once again less than any positive rational number. Does this table also have a value of up? If so, then this red flower with value down would be enough to counterbalance it. But if you try it out, you'll find that it actually takes 2 red flowers to do the trick. Of course, the pair of red flowers has value double down, so the table's value is double up. As we discussed, double up is greater than 0, and it's greater than up. But what about star? The authors of Winning Ways sometimes draw confusing numbers like star as clouds of dust on the number line that cover a certain range of numbers with which they are confused. Now, we need to zoom in on this number line infinitely far to get past all the rationals, but once we do, we can see up and down sitting on either side of 0. And our cloud for star will cover all three of these numbers, symbolizing that star is confused with each of them. Going a little further out along this number line, we get double up and double down. Intuitively, you might think that these numbers would also be confused with star. If single up isn't a big enough number to escape the cloud, why would double up be? It turns out, amazingly, that this is wrong. Up is confused with star, but double up is not. Don't believe me? As always, you can prove it yourself with Hackenbush. This position, for example, has value double up plus star, and you can verify that it's a win for blue, meaning double up plus star is positive. Then, since star is its own negative, we can just move it to the right side of this inequality and get double up is greater than star. Suddenly, we have a much better idea of how big the cloud around star actually is. You might be wondering about the clouds around other nimbers, like star 2 and star 3. Are they just as big as the one for star? Or is the cloud around star 2 maybe twice as big? The answer is neither. In fact, it's smaller. So much smaller that it doesn't even cover up and down anymore. Star is the only nimber that gets confused with up and down. Star 2, star 3, and so on are all closer to 0 in a sense than star is. Are there any other clouds out there as big as stars? Or bigger? Yes, actually, there's clouds of all shapes and sizes, including many you don't even need to zoom in to see. And these clouds, and all the complexities hidden inside them, are a huge part of combinatorial game theory. But in order to tackle that, we have to take a much-needed interlude, leaving these whimsical pictures behind for just a second to get to the real mathematical underpinnings of everything we've been talking about. There's a beautiful, magical, unifying theory behind all these numbers, allowing us to dissect them to their very basic essences, including not only star, up, and their mysterious families, but integers, fractions, everything in between, and more. Strap yourselves in, because things are about to get surreal. Up until now, our approach has been basically to define the values of positions in terms of numbers. But every now and then we've encountered positions that don't seem to fit with any numbers that we're familiar with. So we've had to just hypothesize new numbers on the fly, like star and up, to fit in with our theory. What if we're going about things backwards? What if instead we define numbers in terms of positions? Where would we start with that? Well, let's look at the simplest, most trivial Hackenbush position first, the empty position, with no branches. Neither player can move, and so we say that this position has a value of 0. But why? Well, what if we simply define the number 0 to be the value of a position with no possible moves? Does this make sense at all? Maybe not yet, but let's keep going and see what happens. For where we're going, we're going to need some shorthand. We'll use curly braces to denote the value of a position in terms of its possible continuations, with a vertical bar inside to separate blue's options from red's. Since our 0 position had no continuations, we summarize its value like this. This will be our working definition of 0. You'll get the hang of this notation with a few more examples. We started out our whole mathematical journey by declaring that this blue branch had a value of 1. But again, why? Well, let's just define 1 in terms of the possible moves from this position. Red has no moves, and blue's only move takes us to the 0 position we just talked about. What if we say the number 1 is, fundamentally, the value of a position like this? Again, we'll use this vertical bar notation. From this position, the only possible continuation is for blue to take us to 0. This will be our definition of 1, with 0 on the left of the vertical bar, and nothing on the right. We'll add another blue branch for our 2 position, and set up our curly braces again. Blue has 2 possible moves here, each of which takes us to a 1 position. So we could define 2 to be like this, with 2 1s on the left of the vertical bar. But these 2 1 positions are essentially identical, so for simplicity's sake, we'll just say that there's only 1 possible move, and define 2 like this. And we can keep going, defining 3 in a similar way, and then 4, and so on, each natural number defined recursively in terms of the one before it. This process is analogous for negative integers. -1 is defined as the value of a position like this one, where blue has no moves, and red's only move takes us to 0. From there, we get -2, -3, and so on. If we carry on like this, starting from absolutely nothing, what we end up with is a perfectly valid way of defining the integers in terms of the ways in which games play out. In fact, we've pretty much abstracted away from Hackenbush itself. We can use this system on any games that have positions like these. And this is part of what makes combinatorial game theory so powerful. So we've got all the integers now, but what about fractions like 1/2? Once again, we can go back to Hackenbush. We figured out through experiment that this blue-red tree had a value of 1/2. But now, just looking at the possible continuations, blue's only move takes us to 0, while red's only move takes us to 1. In our vertical bar notation, we get 0 on the left side of the bar and 1 on the right. And this is the canonical way of defining 1/2. As we saw before, we get 1/4 by adding another red branch. Looking at the moves, blue still has just the 0 move, but red now has the choice of chopping this branch taking us to 1/2, or this one taking us to 1. Once again, we have two numbers on the same side of the bar, and we could define 1/4 like this, but we can simplify things again, this time by discarding the 1. If you think about it, red wants the value of this position to be as low as possible, so given the choice between 1/2 and 1, they're never going to want to pick 1. So the value of the overall position doesn't change when we take that option off the table. This expression with 0 on the left and 1/2 on the right is our canonical definition of 1/4. And this pattern continues for all the dyadic fractions. Great, so we've got integers, we've got fractions. We're on a roll now. What's next? Well, remember all those weird star numbers and arrows that we had to just pull out of thin air before? The beautiful part is that now we have ready-made definitions for all those things, based on the corresponding positions and their continuations. And we've done most of the work already. It's time for a speed round. Here we go. So this is the position we said was star. Here each player has only one move, and it's the same move, taking us to the 0 position. Star is what we get when we put a 0 on the left of the bar, and a 0 on the right. Next up, star 2. Here each player has two options which take us to 0 and star respectively, so this is our expression for star 2, with both a 0 and a star on both sides of the bar. From star 3, each player has three options, which take us to 0, star, and star 2 respectively. And in general, the definition of star n involves all of the previous stars less than n on both sides of the bar. No problem, our notation is flexible and powerful enough to handle anything. Here's the position whose value we called up. What's the formula for up? Easy, let's figure it out. Blue has three possible moves. This one takes us to this position, which we know is 0. This one takes us to star. This one takes us here, and red can do these two as well. And I guess this position's value is, well, blue has two possible moves here, and okay, this is starting to get complicated, but this is another huge perk of our recursive definitions. If we don't know the value of a position, we can just look at all its continuations, and then all those continuations and so on all the way down. The result might not be pretty right away, but part of the fun is figuring out all the ways you can simplify things. It turns out that there's a much cleaner way to define up, for example. It's the value of a position where blue's best option is to go to 0, and red's is to go to star. Here's the thing. There is no such position in Hackenbush. Or if there is, I sure couldn't find it. But that's okay. There comes a point in every mathematician's journey where the system they created to explain something takes on a life of its own, far beyond its original purpose. Hackenbush is a great game for introducing some of these mathematical concepts, but like all of the games presented in Winning Ways, it has its limits, and it only gives us a glimpse at the whole picture. You see, I pulled a sneaky on you. This video isn't actually about Hackenbush. It's about combinatorial game theory. The cute, colorful pictures were just there to lure you in. But you're in too deep now, and if you've got a mathematical mind, this is where your heart starts to race, and you get the insatiable urge to just set aside the games entirely and focus on this notation, trying to figure out how it works and seeing just how far we can take it. If you can put literally any sets of numbers on either side of the bar, then there's like a gajillion things you can try, and it's hard to know where to start. It's like a big game of little alchemy that the universe set up for us, where you keep creating new numbers by mixing other numbers together. The rest of this video will be a brief, cursory tour of just some of the many directions in which this revolutionary system can be taken. We'll stick with Hackenbush as our game of choice for illustrative purposes, but we will need to stretch it a bit sometimes to suit our needs, and some of the stuff we'll touch on will go beyond what this one little game can do. But we'll start simple, leave all the stars and arrows behind for now, and go back to good old blue and red trees, but with a little twist. We've seen that this position with a single blue branch has value 1, but adding a red branch on top reduces it to 1/2. Adding a blue one on top of that brings it back up a bit to 3/4, and a red one on top of that brings it down to 5/8. If we keep doing this, alternating between blue and red branches, we'll find that each additional branch has a smaller and smaller effect on the overall position, since the most important branches are the ones near the bottom holding everything up. Indeed, the value of the position will start to converge, getting closer and closer to another fraction, of the kind we haven't seen yet: 2/3. If you're a seasoned math student, it'll be only a small step for you to declare that maybe 2/3 is the value of the infinite Hackenbush position where these blue and red branches go all the way up forever. Can you really play Hackenbush on an infinitely large tree? Why not? All it means is you have that many more branches to choose from. In this position specifically, it's even less complicated because wherever you choose to chop, no matter how high up you go, when that branch comes down, so will the infinitely many branches above it, and the resulting tree will be finite. You might find it a fun little exercise to verify that this infinite position does, in fact, have value 2/3, by demonstrating that 3 copies of it are enough to balance out 2 red branches and guarantee a win for whoever plays second. It's just kind of miraculous how all this works out, isn't it? But okay, how do we write this in our vertical bar notation? Like always, we look at the possible moves for each player. Starting with blue, they have the option to chop here, taking down the whole tree and reducing to 0. Or they can chop here, leaving 1/2, or here, leaving 5/8, and so on. They have infinitely many options, but that's okay, put them all on the left side of the bar. Red, in turn, can chop here, leaving 1, or here, leaving 3/4, or here, leaving 11/16, and so on. This strange pair of infinite sequences is our canonical definition of 2/3. And one thing you might notice is that both of these sequences approach 2/3, but they do it from opposite directions. In the world of finite Hackenbush, the only fractions you can get are the so-called dyadic fractions, whose denominators are powers of 2. But when you allow infinite towers of branches like this, you can not only get thirds, but also fifths, sixths, whatever you want. In fact, you get more than just all the fractions. You get all the other real numbers. Irrationals, transcendentals, you name it. The reason is that, like 2/3, any real number has these kinds of sequences of dyadic fractions which approach it from both sides. And these sequences can then be trivially transformed into a string of blues and reds, like this. In fact, these blue and red strings are pretty much exactly what you get when you write these numbers in binary. Here's pi in binary. And here's a Hackenbush position with a value of pi. However, this process does not always work in reverse. What about a position that's just an infinite stack of blues with no reds at all? Here, blue's only quandary is just how many branches they'll leave for themselves after the first chop. And the sky's the limit. The options are 0, 1, 2, 3, and so on, forever. In our vertical bar notation, we have all the natural numbers on the left side of the bar, and nothing on the right. This is a huge advantage for blue. In fact, it's bigger than any finite number. This number is called omega, and if you've watched a certain Vsauce video, you'll be getting flashbacks to the absolute madness of infinite ordinals. Suffice to say, all that stuff is here, and all those crazy omega expressions have corresponding Hackenbush positions. But those expressions are only a tiny portion of what's possible with omega. Throw away Cantor and submit yourself to Conway, and you'll find stuff like negative omega, or the square root of omega, or the omega-th root of omega. Basically anywhere you can put a real number into an expression, you can just shove an omega in there instead. The values of these kinds of expressions, the reals along with all the omega stuff, together comprise what are called the surreal numbers, and each of them has a corresponding Hackenbush position. Surreal numbers are fascinating, they're elegant, and they're a whole video topic unto themselves. But even they aren't enough to fully tackle the strange and loopy world of infinite Hackenbush. about a flower with a blue stem and an infinite number of red petals? What's the value of this position? Well, let's see. If it's blue's turn, they chop the stem and reduce to 0. If it's red's turn, all they can do is chop one of the petals, leaving infinitely many left. The position hasn't changed at all, and it won't change no matter what red does. The value of this flower is 0 bar flower, or using substitution you could express it as 0 bar, 0 bar, 0 bar, 0 bar, and so on, forever. What are we supposed to make of this? Well, stepping back a bit, we can see that even with infinitely many red petals, this flower is still a win for blue, being the only one who can end the game. This means that the value is positive. But how positive? Well, you might be used to this by now, but it's less than 1, and 1/2, and 1/4, and all the positive reals. And not only that, but it's less than 1 over omega, which we call epsilon, and it's less than epsilon squared, and epsilon cubed, and epsilon to the power of omega, and all the other positive surreals as well. However, and get ready for this one, it's greater than up. It's also greater than double up, and all the multiples of up, along with star and all the other numbers. It's kind of a happy medium between the surreal infinitesimals and the even further beyond surreal ones which are even somehow closer to 0. We need a name for it, and because it's bigger than up, we'll call it over. Of course, there's a negative version of over, which is appropriately named under. How about this bit of blue grass with infinitely many blades? This one is even simpler. Blue is the only one who can move, and like the infinite flower petals, each blade we chop brings us right back where we started. The value of this grass is grass bar nothing. Or you could write it as bar, 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 you get the idea. This time, the advantage for blue is a bit more pronounced. They essentially get a free win. No matter how much red stuff you add elsewhere, blue is always going to be able to move. So this value is greater than all the real numbers, and all the surreal numbers, and certainly greater than any amount of stars and ups. At this point, we've almost run out of prepositions with antonyms, but we'll call this gigantic number on, and its negative equivalent off. On and off are not nearly as well behaved as the other numbers we've seen so far. For one thing, you can't do traditional algebra with them since adding stuff to them doesn't change their values. On plus 1 is still on, as is on minus 1, on plus a million, on plus omega, and even on plus on. Holy hell. There is one exception. If you add on plus off, the result is neither on nor off. It's also not 0. Which means on and off aren't really even negatives of each other in the classical sense. What you get by adding on and off is a position where each player has infinitely many branches and will never run out of them. The game will never end, neither side will win, and it's just exceedingly boring. Fittingly, the value of this position is called dud, which is also an abbreviation for Deathless Universal Draw. Some of you might not like how numbers such as on, off, and dud disrupt the nice properties of addition, or that they're kind of defined circularly in terms of themselves. There's a simple workaround to this, which is to introduce a condition on what constitutes a combinatorial game. Just like we said that a combinatorial game involves 2 players and has no randomness and all that, another common stipulation is that combinatorial games can't go on forever. As long as this is enforced, we can have all of our nice omega stuff and stars and bars without having to deal with anomalies like on and off. But if you're feeling brave and you decide to embrace these so-called loopy games, you can dive headfirst into the world of on, off, dud, over, under, and there are many strange relatives, including up on, hot, oh no and oof, high and low, and eventually an entire house of cards. Ace, deuce, joker, and so on, with of course the usual 4 suits all in the mix. Ever wondered what 5 of clubs plus 4 of diamonds is? Now you can figure it out. You'll learn to see the onsides and offsides of every position, how the downsum absorbency rule applies to games of various degrees of loopiness, the curious cabs of abnormal Illinois, and precisely how many servants you need to have on hand when you employ the swivel chair strategy. How about this? Did you ever play that game as a kid where you say is not, and then your friend says is to, and then you say is not over and over again? Well, Winning Ways has you covered. They'll tell you all about the intricate strategy of this game and its mathematical significance. As they'll explain, some loopy games are only latently loopy, while others are patently loopy. But a select few, like the game of Tizen, are blatantly loopy. When you've been immersed in this loopiness for long enough, all that Omega stuff starts to seem pretty tame by comparison. Soon you'll find yourself retreating to the calm, relaxing realm of surreal numbers just to cool down. And I guess what I'll say is, feel free to chill while you can, because things are about to really heat up now. When John Conway first introduced surreal numbers in his book On Numbers and Games, he didn't talk about Hackenbush, or any games for that matter. He defined the surreal numbers using his vertical bar notation, but with a specific restriction. The numbers on the left side of the bar must all be less than the ones on the right. So for example, you can have 0 bar 1, but not 1 bar 0, or for that matter 0 bar 0. If you think about it from a Hackenbush perspective, 1 bar 0 would be a position where blue can win by going to 1, but red can also win by reducing to 0. In other words, it's a win for whoever goes first, which we know can't happen with a regular blue and red tree. In fact, what is 1 bar 0? It's not positive, not negative, not 0. Is this ever gonna stop? Alright, never mind all that. Here's a happy little Hackenbush house with a cracked roof. These dotted lines are just like normal branches, except they're fragile, meaning neither player is allowed to let them fall down. For example, if it's red's turn, and they chop this wall, blue is not allowed to chop the other wall, because that would detach the roof from the ground. In fact, blue can't move at all in this position. They'll have to wait until red takes down their part of the roof first. As soon as they do though, blue will get a bunch of free moves. Since blue can't move here, and red doesn't want to move, this is a 0 position. However, if blue gets to chop down their wall first, then all of a sudden it's red who has to wait on blue. Here, blue is the only one who can move, and their move will take them to a 0 position similar to the one we just saw. The value of this position is 0 bar nothing, which we know from our definition is 1. Putting it all together, from the start, blue can chop their wall to get to a 1 position, whereas red can chop theirs to get to 0. You can check that chopping the wall is indeed the best option for each player, and so the value of this house is 1 bar 0. If we make the roof a little bit bigger, we can increase the incentive for blue. Now the value of the position is 2 bar 0. What if we make it bigger for red? Now red's incentive increases and the value becomes 2 bar negative 1. At this point, the players are just itching to be the one to chop their wall, and the wider the roof gets, the more urgent it becomes to do so. We can produce a position with value n bar negative m for any natural numbers n and m, simply by putting n blue branches and m red ones on the top of the roof. But what do these values mean? If they're not positive, negative, or 0, then where are they on the number line? Well, hey, remember all that time ago we talked about star and what it looks like on the number line? We drew a little infinitesimal cloud covering 0, signifying that star is confused with 0? Well, it turns out that 2 bar negative 1 is confused with a whole lot more than just 0, and its cloud is quite a bit bigger. It extends out past negative 1 on the left and 2 on the right, and it covers every number in this range. 2 bar negative 1 is greater than all these numbers, less than all these numbers, but confused with everything in between. Naturally, adding something to 2 bar negative 1 means moving the cloud on the number line. Adding this extra blue branch, for example, turns the position into 3 bar 0. The cloud still covers 0, meaning that this extra branch is not quite enough to negate the first move advantage. Red still wins this position if they get to chop the wall. Likewise, adding 2 extra red branches doesn't stop blue from winning if they have the move. But if you add 3 red branches, suddenly the cloud becomes uniformly negative, and no longer confused with 0. And as soon as this happens, blue's chances of winning go away, even if they get to chop their wall. On the other hand, 2 blue branches is enough to make the cloud uniformly positive, meaning blue wins even if red goes first. Numbers of the form a bar b, where a and b are surreal but a is not less than b, are called switches. And perhaps the most important property of a switch is what's called its temperature, which is basically the radius of its cloud. The bigger the cloud, the hotter the position, and so the more each player wants to move in it, appropriately enough. If you have a sum of switch positions, like say these 2 houses here, you always want to move in whichever position is hotter. This concept of heat is kind of the missing piece that makes combinatorial game theory truly universal. Most games have some situations where there's an incentive to move, and it's appropriate that so much of winning ways is about how to handle the heat. As you'll find out, not all hot positions are as simple as these switches where after the first move, the position immediately becomes cold. After a while, you'll have to abandon the primitive cloud illustrations in favor of these nifty-looking drawings called thermographs, which describe how a given hot position responds to the so-called cooling process. After enough cooling, these positions all reach their freezing point, and you can also reverse this cooling process and track these trajectories as they go backwards in time. In the heat of battle, you'll learn about tolls, timers, and tallies, the difference between equitable and excitable positions, the kinds of tiny particles that are emitted when games get heated, and how ambient temperature factors into the thermostatic strategy, or, as it's more commonly known, the thermostrat. By the end, even if you lose some of the hot battles, you'll know how to win the cold wars. Oh man, there's just so much left in this book that I haven't even mentioned, and my script is nearing 10,000 words. I'm gonna have to do a speed round. Okay, so one of the central concepts in games like Hack and Bush is the so-called atomic weight of a position. Sometimes all you have is a bunch of blue and red stuff, supported by green, so the whole position is a combination of ups and downs and numbers that are all infinitesimal and confused with each other. That's where the atomic weight calculus really comes in handy, but also don't forget about the redwood furniture. It tends to reduce in value. Hey, remember OOF? You ever wonder what the thermograph of OOF looks like? It's right here. The thermograph of OOF.
What's the bottom?
So okay, here's an expanded form of up, which we know is positive but infinitely tiny. What if we lower one of the zeros here to -1? Well, this number is called tiny 1, and it's even tinier than up, and epsilon, and over, and all the other tiny numbers we've talked about. What's tiny 1 plus tiny 1? Is it tiny 2? No, you silly. Tiny 2 is even tinier than tiny 1. There's also tiny 3, and so on all the way down. What about the negative tinies? Well, those are the minies. Did I mention that this book is like a world builder's almanac? Look at this. Math books have no right to look like this. Remember Nim? Well, there's also Prim and Dim. Did you move first in Horsefly? You should have chosen not to move first, since the position of figure 11 is a P position. Because the set of all nimbers is so important, it has a special name. It's called Sunny, and it looks like this. What about the set of no nimbers? Well, that's called Loony. Isn't that just the empty set? Don't we already have a symbol for that? Who cares? Also, this Loony is apparently used for something else too.
Figure 3. Round and round the world with 9 almonds.
Okay, I'm not gonna make any jokes about the colon principle. You can't make me. Fickle, firm, wild, tame, restless. For too long, words like these did not have precise mathematical definitions, until now. These concepts all come together in the pivotal Noah's Ark theorem, which the writers build up to with this full-page illustration of a bunch of animals labeled with math symbols getting onto a boat. The green jungle slides down the purple mountain. I feel like that's a pangram in another language. Some numbers are big firms, others are fickle units. It's usually not that hard to tell which is which. They have this little aside that takes up half a page where they talk about double infinity and an infinite magnification operation, and then they're like, okay, but enough about that, on to the next thing. When your garden is balanced with just as many blue as red, we shall call it a flower bed. So okay, we have epsilon, which is smaller than all positive reals, and we have all the powers of epsilon and stuff, and then we have over, which is smaller than all of those, and then up, and then tiny 1, tiny 2, and so on. Surely there's no end, right? Well, there is. It's the number tiny on, usually just called tiny, and it's the tiniest number there is. For real this time. Can you believe that? Look at this addition table, just look at it. I don't even know where to start with this. Oof plus oof equals off. High plus oof equals hot. And oof. The bottle is 7-Up. It's 7 times up. Yes, they made a 7-Up joke. I guess I pulled another sneaky on you. This video wasn't about Hack and Bush or combinatorial game theory. It was just a book review. But seriously, I can't think of a better introduction to the universe of surreal numbers and their extensions, or really to recreational math in general, than this one, along with John Conway's other works. Until he died from COVID-19, Conway had always been my favorite living mathematician. Not only were his discoveries revolutionary and exquisitely beautiful, not only was he a trailblazer in several emerging fields of math, but he had a perfect sense of humor, and the mind of a teacher and an entertainer. If he had been working with Berlekamp and Guy today, Winning Ways might well have just been a series of memey video essays instead of a 1,000-page book. But as it is, I think the magic of their work has gone tragically underappreciated by the public, and so many people who've become budding math enthusiasts from watching fun YouTube videos just have no idea what these guys were up to their whole lives. More than anything, I think Winning Ways is the purest embodiment of the spirit of math. We have questions about the nature of games, and through our search for answers we begin to examine some of our core assumptions, eventually getting a golden opportunity to lay out a new system of simple rules that lead to an endless cascade of chaotic consequences far beyond the scope of our original inquiry. And that's where the real creativity comes in, and it feels more like you really are just playing games with the universe rather than doing calculations. It really is equal parts discovery and invention, and while it's a rare mind that can come up with new mathematical theory, it's an even rarer one that can really bring it to life the way Conway, Berlekamp, and Guy have been able to do. Alright, I'm gonna have to stop now, because if I keep going I could wax poetic about the spirit of math and the tragedy of its public image all day. Congratulations to you, by the way, for making it through this video. It's a lot to take in at once, but I hope it was worth it. I guess usually this will be the part where I tell you to like this video and subscribe to my channel, but I've never made a video like this before, and I'm not sure if I'll ever make one again. I did spend all this time finding recording equipment and learning how to use the animation software, but honestly it's just because I thought this particular video needed to exist so badly that I was willing to get off my butt and be the one to do it. But now, here it is, so, you know, my job is done. So, instead of subscribing, then go out and read Winning Ways for your mathematical plays. Not only is it a treasure trove of memey content, but it's very reader-friendly, and it holds your hand a lot so you can learn at your own pace. Although actually, if you like the background music in this video, then that might be a reason to subscribe to me, but on my other channel, where I have a bunch of my original compositions, soundtracks, and countless hours of chill piano improv to relax/study to. It might be good background music for when you go and read that book. Besides that, I guess this is it. Thanks for watching, and I hope you enjoyed. Take care.